So today I want to try to find an equation for the area of a circle in terms of its radius, okay? We have equations for rectangles and triangles and trapezoids for their areas in terms of their width and length. I want to do the same thing for a circle, alright? Now if we're going to do this, we're going to find the area of a circle. One thing that's really great isn't just to remind ourselves about other shapes we already know, because these will be very useful in figuring out the area of this. These will be tools to decompose this shape into something more intelligible. But it'll also be great to look at how we figured these out, and then from those techniques figuring out a new technique to figure out the size of the circle, okay? Alright, so let's do that. Let's do a little reminder of what we did here and here and here, and maybe we'll find out some scheme of getting the area of the circle. So what did we do when we looked at a rectangle? How do we figure out the area of this guy? Well, if it was like a 3 by 5 rectangle, it's very, very straightforwardly, we just said, oh, I can cut this into 3 parts right here. Cut the width into 5 parts, and then I see, oh, each of these squares here is a 1 by 1 square, which has area of 1, right? And therefore, oh, if each of these are 1s, then we have 3 sets of 5 of those, or 5 sets of 3. We have 3 times 5, which is 15. And we see that this doesn't just apply to the 3 by 5 rectangle, but to any square of any length or width. Okay? Alright, will this be useful in figuring out the circle? Breaking it up into other little squares like that. Well, I can sort of think of 2 ways of doing that. Like, I sort of impose a grid onto here, like this. And then I try to say, okay, let's only include the squares here. Let's count up all of the 1 by 1 squares that have some of this circle in there. So like all of these squares are included. But none of, but not this one, or that one, or that one, or that one. Okay, well that's nice right there because it gives us an estimate of what the area of the square is. But this is just an estimate right here, right? As in, this is obviously bigger than the actual circle here. You know, there's all of things like this square and this square, which have a ton of area not enclosed by the circle. So I don't think we'll be able to break this guy up into squares. Another sort of idea you could have had is, what if I just try to fill this up with squares, like this? But again, these squares are getting more and more difficult to calculate as I make them like smaller and smaller. I try to shove in more and more here. And still, no matter how many squares I do, there's always going to be some area here that's not fully enclosed, okay? I'd have to sort of count up an infinite number of squares here, and that's not something we are at all familiar with doing, and nothing we can practically do at this stage. So, this method doesn't look like it'll work for a circle. Worth trying, though. Okay, what about triangles? How do we figure out the area of, let's say, this right triangle? Well, the way we did that was, okay, let's take this right triangle, let's make a copy of it, and then we can just spin that around, okay? We can spin that around like this, and then just place it into there. And we get a nice rectangle out of it like this. And we know, oh, a rectangle. I know what the area of a rectangle is. That's width times length. So this is width length, this is width length. Then I see, oh, okay, the area here of, if this is the area, I'm interested in the area of this triangle, then two of those, this one and that one, equal the area of this rectangle, which is width times length. Therefore, area equals width times length over 2. Great. Alright, so the idea here in essence was, well, over here we basically cut this up into a bunch of little squares. The idea here is, oh, maybe we can make a copy of this shape, turn it around, and turn it into a rectangle or some other shape we're familiar with. Can we do that with a circle? Well, not really. I make a copy of this guy. I turn it around. Well, turning a circle just gives you the same circle, so that doesn't really do anything. I mean, if I made a bunch of these guys, I could, like, make a shape, like a trapezoid here, or maybe a triangle. But again, there's all sorts of, like, spaces inside of here that are not getting filled up. Okay, so this method is not working for us. This make copies and then flip them around. Maybe something like that will be useful later, but not as far as I can see. Alright, but also notice one other thing here. When we did this here, we didn't just flip things around and copy them, we also reduced it to a familiar shape. That might be useful later. What about trapezoids? What do we do there? Well, trapezoids have a nice trick to them. Not trapezoids, parallelograms, excuse me. I can just cut off this little edge triangle here and then move it over there. Okay? So now we get a new rectangle here. That where we cut off the side here, move it over there. And oh, that's width times length, right? Length, width. So, okay, this method right here was cut off a piece, move it around somewhere. Okay, can we do that with the circle? Well, okay, let's try it. Cut it in half. Can I do anything with that? Not really. Like, I can do something weird like this, where I like have the round sides against each other, but I don't see how that helps. Okay, maybe the problem is we're not cutting enough. So let's cut it 4 times. Alright, what kind of shapes can I make with that if I rearrange and spin them around? Well, I can make some curve like this, and then like this, then like that, and like that. That's kind of neat, but I don't see that getting anywhere. Just checking battery life. So, what's another idea? Well, what if I take this shape, and then I maybe flip this one, keep that one that way, flip it. Or, excuse me, I'll just show you which I mean. I take one, and I do this. Take another one, have it sort of upside down, fitting that other side. Then I do this one again. Then do that one again. Okay, that seems a little better than this shape over here. This seems a little more useful. I don't really know yet, but at least it's a nice pattern. Okay, what if I did more? What if I cut even more? Had like 8 pieces here. Well, what I'll then have is something like this. If I basically try to continue that pattern there. Excuse me. 1, 2, 3, 4, 5, 6, 7, 8. I'll have these 8 pieces like that. And I'll look at this and I'll feel, you know, this is really familiar right here. This looks like a trapezoid, right? You know, it has this sort of round part on top, but these sides are straight. That looks solidly like a trapezoid. Alright, so roughly what is the size of this trapezoid here? Or trapezoid? Well, let's see. What 2 things do I need to know for a trapezoid? I need to know its width and its length. Okay, what is its width? Well, width is basically how long is this side? Well, I don't really know. It's like this round part right here. So whatever that round part is, which is not quite perfect, it's not exactly this straight line, but it's pretty similar, that round part, right? So I want to find this line, and this round part seems pretty similar. Do I know the length of this round part? Well, how would I get that? Well, basically, I took that from half of the sphere, right? As in, half of the surface ended up down here, half of it, these guys ended up there, on top. So, okay, if the circumference of a circle is equal to 2 pi r, and I'm only using half of the circle, a semicircle here, then that's pi r, so roughly speaking, this length right here is approximated by this round edge, which is pi r. Okay, that's nice. Again, it's just an estimate so far, but it's at least something encouraging. And then, okay, so I've got the width part of this. What about the length? Let's see. Well, the length, I guess if I start off like right here and I go out like that, then that'll roughly be how the length of this trapezoid. What is this right here? Well, that's basically, this comes from the center here, and then it goes out all the way to the circumference. The distance there is r. So this is r. So I've got width times the area of this guy is approximately the width times the length, and those guys are, roughly speaking, r, excuse me, let me write that the other way, pi r, that's what width is, and then the length, which is r, pi r squared. Okay, that seems pretty powerful here, but the thing is this is still just sort of an approximation. This isn't quite perfect here. Isn't there a better way of doing? What happens if I maybe do an even better approximation? You know, cut this up even further. Well, then that would look like something like this. And that right there is almost exactly a trapezoid there. You know, the difference between, excuse me, let me write that a little more neatly. The difference between the radius and that height is almost nothing. There's almost no difference there. The same thing with the difference between this line here and that sort of rounded part on top. You know, it's a little different. Like, this is a little longer, but it's almost the same thing. And what we find is that, oh, if we as we rearrange all these little wedges inside of this circle, as we make it more and more pieces here that we spin around and rearrange like we sort of did with these guys, we get something approaching pi r squared. Right? That's what we are approaching as we do this process more and more. Now, that feels strange, and for those of you who know calculus, this is sort of a limiting process, technically speaking, but the rest of you forget about that. So, it seems like, well, is that quite fair to do that? To just basically say that, well, that's what all of these approximations tend towards as we make more and more cuts, so it's reasonable to call the area that. Well, let me show you a sort of a precedent here, okay, involving the parallelogram, where a similar sort of argument has been used in the past. One way they reasoned that the area of a parallelogram is equal to width times length, is they said, well, what if we made the parallelogram out of a bunch of little squares like this. Rectangles, excuse me. That's roughly the same thing. And then what if we then straightened all of them up? Okay, so we turned this thing into a rectangle like this. Because all of these guys, all of these rectangles, are of the same length. We see now that, oh, this right here is just that length right there. And the width of all these guys are the same. Therefore, length times width equals area. So this was an idea used on parallelograms before, and we're using the same kind of idea here of, oh, let's just cut up this shape more and more. Let's make smaller and smaller edges here. Just like here, we might want to make smaller and smaller little rectangles inside of there. We rearrange them. Here we just move them to the left. Here we flip them upside down and right side up. We fit them together and we got a shape which we were familiar with. In this case a trapezoid, in this case a rectangle. So when you're thinking about why is the area of this shape right here, the circle, equal to pi r squared, the most natural way to remember that, to see why it's true, is, okay, it's useful often to cut up shapes like the parallelogram, and it's also useful to move them around, to rotate them into some other shape. Like that, okay? And then we see, oh, well, the height is roughly or the length is roughly speaking the radius, and this right here, since it's on both sides here, the width is half of the circumference being 2 pi r, therefore it's just pi r. Okay? And that gets us a is equal to pi r squared. So again, the basic idea of how we did this, how we figured out what the area of a circle is first we remind ourselves the shapes we already knew and how we knew them. Whether it was filling it with tiny squares, making copies and turning them, or cutting them up and moving them around. In this case, we sort of used a combination of these two techniques. We got basically this trapezoid here, and we found, oh, just like with parallelograms, where you kind of make them out of tiny little rectangles to make one big rectangle, we can turn this circle into a bunch of tiny wedges, and those wedges we can see are equal to pi r squared. And then as we make those wedges smaller and smaller, the difference between this shape, between these shapes and a parallelogram is indistinguishable. Okay?